friends. In the previous lecture we got into the basics of vectors. Even though it is something that you have been dealing with from your school days, we looked at in relation to the different ways of representing, or one of the ways of representing the concentration of an alloy. Now we saw that when we consider the representation of a vector, it is based on an orthonormal basis, and this orthonormal basis can be extended to form a vector space. And the difference between an orthonormal basis and that translating into a vector space which involves or which can be related to that of an orthogonal system, we saw it in our previous discussion. Now when we are able to represent a concentration of an alloy in the form of a vector, what it allows us to do is, it allows us to represent this concentration, or it allows us to indicate this concentration in a given vector space. Now if you consider a manganese steel that typically comprises of iron, carbon and manganese. Now the independent concentration variables that are sufficient for us to describe the concentration of this manganese steel are the concentration of carbon and manganese. So it means that it is possible for us to treat the concentration of this manganese steel in terms of just carbon and manganese alone. So essentially we need, if we are able to develop a two-dimensional vector space, then it will be possible for us to represent the concentration of this manganese steel in this two-dimensional vector space. Okay, if we construct a vector space of this form, wherein one basis represents the concentration of carbon, the other represents the concentration of manganese, each point in this vector space indicates a definite concentration of a manganese steel. So here this indicates a manganese steel with concentration C1 and M1. So Mn1, meaning this point here, it indicates an alloy with a concentration, a carbon concentration of C1 and a manganese concentration of Mn1, and this point it indicates the manganese steel with concentration C2 and manganese, amount of manganese Mn2. So what it allows us to do, the treating or translating or handling the concentration of a given alloy, a given, in this case, a ternary alloy, as a vector, it allows us to represent the different concentration in a given vector space. Now the reason we want to do this is because, given that it is a vector, it is also possible for us to extend the nature of this vector, extend the dimensionality of the vector. What can be done is, we can augment we can include in this representation the yield strength of this vector. So Ys here represents the yield strength of the vector. I hope you are able to recollect what an yield strength is. It is one of the ways of describing the mechanical properties of a given alloy. So in this case, we consider for this manganese steel, we consider yield strength to represent its mechanical property. Now of course, as being from a materials background, we know that depending on the concentration, the yield strength would vary. So therefore, what essentially it means is, now in addition to the concentration, we can include this yield strength in an additional dimension, and we can represent this entire combination of concentration and its property in using a single vector. Let me repeat, what essentially we are trying to do is, we want to represent the concentration of an alloy using or in the form of a vector. When we did that, it allowed us to represent a concentration as a point in a given vector space. So in this case, this we were able to do because we were able to translate a concentration into a vector, and when we do that, we were able to represent a given concentration as a point in a vector space. Now what we are essentially trying to do is, we are trying to augment to that concentration. We are trying to add an additional dimension to that concentration. So similar as it is the property of a given alloy, as the concentration is a feature of a given alloy, a property of a given alloy, so is its yield strength. So therefore, what can be done is, we can also append another dimension, another property to this vector. So initially, we saw that one way of representing a vector of this form, that is Ai, Aj and Bk. A vector of this form can be represented as Ai, Aj, Bk as a column matrix. In the same way, this concentration, the ternary concentration, can be represented as initially as C and Mn. Now this is a two-dimensional vector. This creates a two-dimensional vector space. Now to this, what we are trying to do is we are trying to include the yield strength as well. So this then extends to a three-dimensional vector space. Again, this yield strength is a characteristic property of the alloy because it is dependent on the concentration. Now once we are able to create such a representation that includes both concentration and one of the mechanical property, then what can be done is we can create a corresponding vector space, a three-dimensional vector space, wherein in addition to concentration, that is C, Mn, we have the yield strength, the property, the characteristic property of the specific alloy being included in this vector space. So we have now moved away from two-dimensional vector space to three-dimensional vector space by considering another feature or another property, that is the yield strength. Now each point in this vector space, it represents not only the concentration but also the yield strength associated with that particular alloy. So we have an alloy. The characteristic feature of an alloy is that it has a specific concentration. Because of that concentration, you have an yield strength. Of course, assuming that all these alloys are exposed to the same processing technique. So whatever processing technique one alloy is exposed to, the other alloy is exposed to as well. Meaning all the other variables are constant. So now the yield strength is exclusively governed by the concentration. That allows us to create a matrix like that, and through that matrix, or that allows us to create a column matrix like that, a vector of this form, and through that, using this vector, we have created a corresponding vector space. And now each point in this vector space, what it represents is, it just not only represents the combination of different concentration, but also the yield strength associated with each of these concentration. Now, when we have sufficient number of such points, wherein we have related both the concentration, and where this vector space includes concentration and also yield strength, what we can do is, it is possible for us to fit rather a surface that includes all these known data points. So what essentially we have here is, we have a three-dimensional space, and in this three-dimensional space we have definite points, and each of these points, they include both concentration and yield strength of different ternary alloys. And what essentially we are doing is, using these known points, we have fitted a surface, a two-dimensional surface. The red line is a two-dimensional surface, a two-dimensional plane or a two-dimensional surface. Now, when you are able to fit such a two-dimensional surface that is based on the known alloys and their corresponding yield strength, if we are now able to describe this surface, if we are able to rather accurately describe this surface, what it allows us to do is, it allows us to predict what would be the yield strength of the alloy that is of the known composition. Let me repeat, we have certain number of known points, we have certain number of known alloys along with its yield strength, and we use this vector space and position those points in this vector space. And once we have positioned those points, we are fitting a two-dimensional curve through it. Now, once you have fitted a two-dimensional curve through it, you are attempting to describe this two-dimensional curve. This two-dimensional plane, this two-dimensional curve, you have made it known through, or you have described it through an appropriate expression. Once this two-dimensional plane is known, once you are able to describe this two-dimensional plane, then supposing if you have just the concentration alone, supposing if you know just the concentration alone, then it becomes possible for us to place that appropriate concentration in this plane here, and we will be able to rather predict what could be the estimated yield strength for that concentration. So if I am able, only for me just the concentration here is known, then when I place the corresponding concentration here, then using the concentration, it becomes possible for me to predict what will be the corresponding yield strength. This is possible only when I am able to extract this two-dimensional plane, when I am able to describe this two-dimensional plane. So what essentially I am able to do is, when I am able to describe a two-dimensional plane that passes through all the known points, it becomes possible for me to predict what would be the yield strength of an unknown alloy. So what essentially it means is that this forms, or this approach helps us build a predictive model. And this predictive model is possible because we have appropriately translated, or we have appropriately handled our concentration in such a way that it becomes possible for us to represent the concentration in the corresponding space. So once we are able to handle the concentration in a way that it becomes possible for us that each concentration is a point in a given space, then it is possible for us to fit a plane through that particular space, so that that plane includes all the known points. And once I'm able to do that, then it is possible for me to describe that plane, and using that plane, then I'll be able to predict what would be the yield strength if the concentrations are known, and this forms the basis for the predictive model. And now if you use machine learning tools to rather fit this plane onto this known points, then this will yield a machine learning based predictive model. So this forms the fundamental for developing a predictive model that helps us rather predict what would be a given property of an alloy for a given concentration. So this is how at least the framework or the outline of it, this is how it works. So if you use a machine learning tool in order to describe this particular plane, we refer to that as a machine learning based predictive model. Now, so far what we have considered is, we have considered a simplistic case of a ternary system, and we have augmented a yield strength to it. Now if you build, or if you consider an even more complex case wherein instead of ternary system, what you have is a quaternary system wherein you have iron, carbon, manganese and chromium. So you are getting close to the stainless steel, typical stainless steel concentration. So what essentially you have is, you have, in addition to manganese, you also have chromium. Now in this case, the number of independent variable is 3. So ideally, even without augmenting any mechanical behavior or any mechanical property to it, you need to have a 3-dimensional space to represent the concentration here. So without any mechanical properties augmented to this system, you already need a 3-dimensional space. Now if you include the mechanical properties, say yield strength here, what you need is a 4-dimensional vector space to represent the concentration along with the property. Now of course it is rather not possible for us to draw a 4-dimensional space, but like we considered earlier, it is possible however to handle such a space for us numerically. So even though it is rather difficult for us to rather plot or illustrate it as a 3-dimensional space, but it can be handled numerically. So when we handle this numerically, when we take the similar approach, when there is sufficient number of known points, that is, we have sufficient number of data points that includes the concentration of this quaternary alloy and also the corresponding yield strength, then what we can do is, we can now fit a similar plane. So this plane now would be in 3 dimension, and in this case we refer to it as the hyperplane. So now it is possible for us to fit an hyperplane through this data points, and once we are able to fit such an hyperplane and describe it, then we will be able to again build a predictive model for a multi-dimensional. So this is beyond a 3-dimensional. So this is a multi-dimensional. Of course, you can also have another composition here. So therefore, it is possible for us to build a predictive model for a multi-dimensional data set. So what essentially it means is that here we have restricted ourselves to a quaternary system, meaning 3 independent variable or 3 independent concentration. There can be any number of concentration, there can be n number of concentrations. So if you consider x1, x2, so on and so forth as concentration, there can be n number of concentrations, and there can also be any number of properties that can be included. So irrespective of it, so for this discussion, let us restrict ourselves to one property. So we have the concentration represented here, and we have the relevant property associated with it. Now, irrespective of what is the number of concentration that is involved, again, since we have handled this concentration and the property in such a way that it is possible for us to represent the concentration and the property in a space, in a multi-dimensional space, then it becomes possible for us to fit an hyperplane through it. And if we are able to describe the hyperplane, we will be able to predict the property associated with a alloy with n number of alloying elements present in it, and we will be able to develop a predictive model. Of course, like we saw, developing or describing this hyperplane will not be straightforward, so we need sophisticated techniques, sophisticated machine learning techniques, and when we use these sophisticated machine learning techniques, so what essentially we end up having is we end up developing a machine learning based model or a machine learning model that is predictive in nature. So this is the role that the handling concentration as a vector plays a role when we are considering it in a framework of the data analysis or in the framework of the machine learning. Now this all has to do with the basic understanding of the vector space and how we represent a vector. Now if you could recollect, there are other features of vectors, the other properties of vectors that we also use in the while understanding the behavior of materials, while describing the behavior of materials. Now if you could recollect when we described the different components of stresses, when we want to rather describe the mechanical condition experienced by a material in a real life situation. What we mean by a real life situation is often when we talk about the mechanical condition experienced by a material, when we talk about or we introduce the mechanical testing of materials, the mechanical behavior of materials, we consider the loading conditions that are rather pristine, that are rather ideal. So what I mean by that is whenever we introduce the mechanical behavior or whenever we introduce what a mechanical condition is, whenever we talk about what a tensile loading is, we consider a sample of the sort, and the loading condition is often considered to be like this. This would be an ideal tensile loading condition. However, this is not usually the case. What we often observe is if you have a plane of interest, a region of interest, the mechanic or the condition that a component in an application would experience is not always along, or it's not always as ideal as the tensile loading condition. It is not always along one of the axis of the coordinate system. It is not as ideal. So what we observe in an application is a given material. It would be as straightforward as a cylinder like this. Often a cylinder like this experiences stress not along the specific or the principal axis, but it experiences load along an inclined direction. So we need to understand or we need to describe in a way that is possible for us to handle such a loading condition. We need to describe this load in such a way that it is possible for us to handle it, to describe it. So essentially what we try to then do is we try to rather split this load into different components, and in order to do that we consider the angle of inclination with respect to its normal. So we have a region of interest and we have a normal to the region of interest, and we consider how it is inclined. Ideally the tensile loading direction should be along this normal, so that is what the ideal condition is. But now we have an inclined loading direction, so the direction is another inclined. Now what we want to do is, in order to describe the loading direction or the loading condition or the mechanical condition experienced by this region of interest, which is now experiencing a load in the inclined direction, we consider the normal, the ideal direction along which the tensile load should act, and we can quantify the angle of inclination, and that we refer to as the theta. Now when we want to understand how much of a load is experienced along the normal direction, what we did or what can be done is we can project this load onto this direction. So again, if we want to know how much of the load is acting along this direction, then what essentially we can do is we can project this load onto this direction, and one way of doing that would be taking the dot product of two vectors. So when you take the dot product of two vectors, what essentially it gives us is, it gives us what is the component of one vector acting on the other vector. Say for instance, to put it more generally, we have vector A and vector B, and you want to know what is the component of vector A acting along the vector B, then what you essentially do is you take the dot product of A and B vector. Now of course this is we use a dot here, that is typical of the name dot product, and I have once come across a paper wherein they have represented the dot product as something like this, and only later I came to know that this is Dirac way of representing the dot product, and it is largely used in quantum mechanics, the field of quantum mechanics. And of course, we now are entering into the world of quantum materials. So if in future, if you pursue a research in quantum materials, and if you find such a notation, please note that this is nothing but our dot product. Okay, so this is one way of representing the dot product. Irrespective of the way you represent it, the fundamental concept behind remains the same. That is, the dot product enables us to project one vector onto another. Now, the way we represent it, if you could recollect how we handled this, how we were able to estimate what is the amount of load that is rather being imposed in the normal direction, we considered it to be p cos theta. We were able to do that by some trigonometric operations, like dropping a normal from here, and this forms a right angle triangle, and cos theta would involve the plane that we are interested in. So therefore, essentially, the dot product, so if you have this A vector is represented by AI, AJ, and AK, and similarly the B vector is represented by BI, B, and BK. Now the dot product of A vector dot B vector would be AI, BI, AJ, BJ, and AK, BK. So what essentially we have is, when we know the expression, this expression of the vector is known, the dot product can be written in this manner. And what essentially this means is that we don't still have any directions associated with any orthonormal basis associated with the dot product. So what dot product ultimately gives us is a scalar value. So this is something that you might already have learnt about. So what essentially then we have done is, this is the direct expression for the dot product. And now when we consider the dot product as a projection of a vector onto another vector, in that case the dot product can be written as the magnitude of the A vector and the magnitude of the B vector and the cos of the angle between these two vectors. So the dot product is, particularly when you are considering it as projecting one vector onto another vector, then dot product is the product of the magnitude of each of these vectors and the angle separating them. Now, if we know what the scalar value of the dot product by this expression here, if we know what is the scalar value of the dot product and what is the individual magnitude associated with each of these vectors, then it becomes possible for us to calculate the angle of inclination. And now that we have involved theta here, then what essentially it means is that the dot product will be maximum and the theta is 0 when both these vectors are pointing along the same direction, and it will be 0 when both these vectors are perpendicular to each other. So the extreme cases are when theta is 0 and theta is 90 degrees, and this here would be maximum and it is going to be minimal or 0. Now again, the reason why we have theta, cos theta here, not sin theta but cos theta here, can be understood by few trigonometric consideration, like again, if you construct right angle triangle, that is the way we will be able to relate this side to that of the other side that needs to be projected. Now what essentially we have done is, we have now written down the dot product when we are considering the projection, but we don't really know what these terms are. Again, we have just stated that these are the magnitude of each of these vectors respectively. So this represents the magnitude of A vector and this represents the magnitude of B vector, but we have not arrived at an explicit expression for these magnitude. So the way we can arrive at or estimate this magnitude is rather by considering the dot product of a vector to itself. That is, when I consider the dot product of a vector to itself, what essentially I would end up having is, I would end up having a vector that is of magnitude a square. And now when I take the square root of it, then ultimately what I would end up having is, I would then end up having estimating the magnitude of a vector alone. So what the magnitude of the vector is, so how the way the magnitude of a vector can be estimated is by considering the dot product of a vector to itself. And when you consider the dot product of a vector to itself, then it ultimately offers, or it ultimately renders a square of the magnitude, and you need to take a square root of it, and ultimately you will then be able to estimate the magnitude of a given vector. And this rather representation and this magnitude of the vector is referred to as the norm of the vector. So this way of representing, or this represents, even though it represents the magnitude of a vector, the way we describe it is, we describe it as the norm of the vector. Now, when you consider the ratio, that is a vector and the norm of the vector, what you end up having is a unit vector that is pointing along the a direction. Supposing you have a three-dimensional, so we consider a vector of this sort. So this is our a vector, and this is in the orthonormal basis of I, j and k. Now what essentially we have done is, we have taken the ratio of the a vector with respect to the norm of the a vector. So what it then indicates would be a normal, or rather a unit vector along the a direction. So it will be along this vector, that is the ratio of a vector to its norm. The norm is, again, since we are taking the dot product, the norm is a scalar. It just considers the magnitude of the a vector. So norm is a scalar because we are considering the dot product of a vector to itself, and we are taking the square root because we have to sufficiently relate, or appropriately relate the output or the outcome of this dot product to the magnitude. So we are taking the square root of it. And now when we do that, what essentially we end up having is, we end up having a norm of the vector. So when you consider the norm of the vector, which with respect to its original vector, what the norm of the vector is just the magnitude of the vector. Now what you are doing is, you are taking the ratio of the actual vector, the a vector, to that of the norm of the vector. Then what it represents is a unit vector along the direction of our original vector, and this is what we refer to as the normalized vector. Because we are dividing it by the norm we are representing, or we name it as a normalized vector. So normalized vector is nothing but a unit vector along the direction of a original vector that has a definite magnitude to it. So a vector has a definite magnitude associated with it, and the norm of this vector, it allows us rather to estimate, or when you normalize this particular vector, it allows us to have a unit vector that is actually pointing, or that is actually oriented along this direction of the original vector. Now when you consider the dot product of these two, and when you want to express it, what you would end up then having is ai square plus bi square, or rather g square, the whole power 1 by 2. Now again, it is rather vital for us to remember that all this is possible. We are doing all this assuming that what we have is an orthonormal basis. Our I, j and k are perpendicular to each other. So because we have started off from this point here, we are able to do all this, and it is also possible for us, even without considering the dot product of a vector to itself, even using trigonometric operation, to estimate the vector, the magnitude of a vector, and arrive at this relation here, provided we stick to this condition that we are talking about or discussing within the framework of orthonormal basis. Now when you consider the projection of one vector onto another, what essentially we are, the end product of it, when you consider the projection of one vector onto another vector, this one here, the expression that talks about the projection of one vector onto another vector, this one here, what ultimately the end product of it, the outcome of it is a scalar. So what essentially we are talking about is, what is the magnitude of the a vector that is acting along the b vector, or the b vector, or what is supposed to be the direction of the b vector. So ultimately what you end up having is just a scalar value. But when I want to know what is the vector that is acting along the b vector, so what is the portion of the a vector, I don't want to know what is just the magnitude, but I want to know what is the portion of the a vector. So far, since again when you are talking about the mechanical behavior, all that we are interested is in the scalar values, because once we know, we have distinguished, or we are just interested in two direction, that is the normal and the direction on the plane. So once we have identified these two characteristic directions and we know what is the load that is acting along these characteristic direction, that is sufficient for us to describe the mechanical behavior of the material. So for a given specific case, since we have already identified the two specific directions, that is one that normal to the region of interest and other the along the region of interest, this we know, or we describe it based on the fundamental understanding of how we have distinguished the stresses into normal and shear stresses. So once we have identified the specific directions that we are interested in, and once we are able to just measure or estimate the amount of stress acting in the specific direction, that is all that is required for us. Just this is sufficient for us in that case. So it is just sufficient for us just to consider what is the scalar value that is acting in this direction. However, in most instances, in a generalized case, we not only need to project, we not only need to know how much of a value is associated with or how much load is associated in this direction, but what is the end direction. We need to have, when you project, we need to have a vector that is acting along the B direction. So when I project the A vector onto the B vector, in addition to the magnitude, I also need a direction associated with it. So I need, my output should be not a scalar but a vector. So if my output needs to be a scalar, then I can go for this expression here. On the other hand, if my output needs to be a vector, then I need to incorporate the appropriate, or need to extend the appropriate this expression in such a way that the output is rather a vector, not a scalar. So in that case, if my interest is not just a scalar value but my vector that is acting in the direction of the B vector, then the corresponding expression for the projection would be B vector divided by the norm of B vector square. So what essentially this expression would help me do is, it would help me project my A vector onto B vector, and it will enable me to estimate what is the portion of the A vector that is acting along this direction. Just not the amount of A in the B vector, but what is the portion of the A vector itself that is acting along the direction. So what essentially we have here is, the outcome of this expression here is not a scalar but a vector. Now what we have is, this gives us a scalar value. This operation alone, this dot product alone gives us a scalar value, and this scalar value you are multiplying it by the B vector. Now what you have essentially done is, by this operation what you have essentially done is, you have gained two additional B values. So here you have your B value, here you have your B value. So it becomes rather important for us to normalize it, and therefore we have norm of B vector square. So it takes rather the value that is gathered by this B and this B. So we are projecting A vector to the B vector. We only need to know the direction of the B vector. We don't need the magnitude of the B vector. So all we need to know is, we need to know the projection of the B vector. So in that case, what essentially we are doing is, we have achieved the projection here itself, and the direction comes from this vector here. So this vector here gives us the direction, and the combination of it, scalar and the direction, gives us the projection as a vector. Now even though this operation gives us both scalar and direction, there is additional B that is included in it, and in order to get rid of it, we take, or we divide the numerator with the square of the norm here. And when we do that, we are able to express or describe the projection of the A vector that is acting along the B vector as a vector. So we are projecting A vector as a vector itself, and we are describing the portion of the A vector which is a vector that is acting along the B direction. So this expression here, it enables us to describe the projection of the A vector itself that is acting along the direction of the B vector. Now, so this is one of the application of the dot products. When you consider what role does a dot product play, particularly in materials research, so one of the role, apart from the mechanical behavior helping us rather dissociate a mechanical stress or a load that is acting in an inclined direction into its components of stresses, what it allows us, this dot product allows us to dissociate it into different components of stresses. The generalized description for rather projecting one vector onto another vector is this, wherein the outcome is also rather a vector. Now the approximation, when we use the dot product for dissociating the load into the different directions, that is normal and the shear direction, we made some assumptions. We already fixed our directions, and we also assumed that these directions, that is the B vector, are unit vectors. So once we have assumed that these B vectors are unit vectors, that is the vectors along the normal and also along the shear, they are unit vectors, then it allowed us to substitute the B as 1, and all that we are interested was in A cos theta. So when we have such a case, we consider it as P cos theta, and here P cos 90 minus theta. So that is all we did, because we assumed that these two vectors are unit vectors. Again, if you could recollect our discussions then. But in a generalized case, this is how it works. And when we want just not a scalar but a vector that is acting along another vector, then this is the generalized expression associated with it. Okay. So now, in addition to, so essentially when you consider, so before we move to the other operation that relates to vectors, when you consider the dot product A dot B, what essentially we have then is, since we are essentially talking about the projection of a vector, we end up with a scalar value. This is something we considered earlier. When you consider the nature of this dot product, we end up with a scalar value. On the other hand, there is another way of handling or relating two different vectors, and that is what we refer to as the cross product. Again, the cross is involved here in some manuscript. This cross at times is encircled, I've seen, but also this encircled cross has a different meaning, but at times the encircled cross, to differentiate it from a simplest, so when you have a set of expression wherein you have represented the product as a cross and you want to describe it or differentiate the cross product of vectors from a simple product, in a manuscript wherein both these are involved, people have used this cross, a circle. So when you find such an expression, then again it makes the cross product. Now the way we deal with, or the way we handle the cross product is, we handle the cross product in a different manner. We try to build a matrix, again assuming that we use the similar magnitudes for A and B vector. The cross product A cross B, and the cross product can be expressed as the determinant of a matrix, wherein we have our orthonormal basis I, J and K, and in addition to that we have our components of magnitude, that is AI, AJ, AK, BI and BK. Now this cross product, and given that it is the determinant of the matrix here, it can be then represented as cross B, can be represented as I of AJ, AK, BJ, BK. So this is the I vector J. So this would be these two here. We have considered these two here, and now we have to include J, the determinant of J. So therefore AI, BI, AK, BK, and now the kth vector. So we need to consider these two, these two columns, or rather these two rows, or the truncated rows here, that is AI, BI, AJ and BJ. So this is what the cross product of when you expand the cross product of vectors A and B, this is how it looks like. Now of course you can further expand it. You have to multiply this two and then subtract it from these two here. So when you do that, you have a simplistic representation of the cross product of two vectors. So one key point, so one difference that you would observe is, when you have such a representation, the end product of this would be a vector, because we have each of these magnitude, each of these scalar values. So when you consider, so this will expand to AJ BK minus AK BG. So this will be a scalar, and this scalar is being attached to a basis, and this will also be a scalar, and it is being attached to a basis. This will also be a scalar being attached to a basis. So what ultimately a cross product would give you is a vector. Now when you say a cross product will give me a vector, scalar is no problem because scalar is just a magnitude. When you say that the cross product will give me a vector, what it essentially means is that the output of a cross product should have a direction associated with it. Now if you consider these two to be our vectors, say A and B vector, now the cross product of A and B, so again when we say it's a vector and it has a direction, it needs to have then a direction associated with it, then the cross product of A and B will have a direction perpendicular to A and B vector. So the direction of the cross product is perpendicular to A and B, and it follows right hand thumb rule. Right hand thumb rule. So you have to, when you consider how the rotation is, and so if when you move from A to B and your thumb points upwards, so therefore we have A cross B, the direction of the A cross B vector here. So what we have seen is, we have seen what the role of the dot product is, and now the output of a dot product is rather the dot product we use for the projection, and to know the magnitude of a given vector. So that is the role played by the dot product. And the cross product, it considers it considers the determinant of the matrix that we have created, and the output of the dot product is along the normal direction. When you consider geometrically what the dot product or the output of the dot product is, the magnitude that you get out of it, it essentially it quantifies the area that is being enclosed by this parallelogram here. So when you consider the cross product between two vectors, and the direction of the resulting vector is pointing in the normal direction of these two vectors, but when you consider the magnitude, this magnitude it rather quantifies the area that is formed by these two vectors. So when you construct a parallelogram out of these vectors, the area that is enclosed by the parallelogram is the magnitude of these two vectors, and this primarily stems from the nature of the determinant. So when you consider the determinant also can be related to the area of the parallelogram that stems out of the matrix. In the same way, the cross product, it can be described as, or it can be, the geometric meaning of it is the area that is enclosed by the two vectors, particularly the parallelogram that stems out of this two vectors. Now before we end our discussion on the cross product, since the geometrical meaning of the cross product can be related to rather the area of the parallelogram constructed by the corresponding vector, now it is possible for us to drop, for instance, if we have such vectors A and B, A vector and B vector, and the parallelogram is constructed through these vectors. So we have A, B and A vector here. Now it is possible for us to drop a height, and if the angle between these two are theta, and this height would then be represented by sine theta. So correspondingly, when you want to have the way we can, if you just want to estimate the magnitude of the cross product, when you want to know what is the magnitude of the cross product without so much of worrying about the direction, because we already know what is the law that governs the direction. In that case, the magnitude of cross product is A cross B. The norm of it, just the magnitude of it, is nothing but the norm of A vector alone, the norm of B vector alone, and sine of theta. So what we have seen is, we can estimate the magnitude of a cross product again from its geometrical representation, and also we saw that how the direction of the resulting vector, so dot product, it gives us a vector, and how the direction of the resulting vector varies, and what is the rule that needs to be adopted to identify the direction of this vector that results from the cross product of two vectors. Now with this, we would like to wind this lecture up, and in the subsequent lecture we will consider different operations that are related to these vectors. Particularly, we will at least try to learn the basics of grad, divergence, and some points on what a curl is. Of course, these things you already know, but we will try to refresh our understanding of what a grad or the gradient or the divergence and a curl is. Goodbye.